So it's now started. Jamie, floor is yours.
Thank you, and thank you, Patrick, for inviting me to this. My name is Jamie Tucker-Foltz. I'm going to be talking about some. I'm at Harvard University, advised by Ariel Pakacha, and I'm going to be talking about some ongoing and recent work that I've done with my advisor on political redistricting math stuff. I'm going to try to give a general overview of this research area and also focus on one of my recent papers as well. So the agenda for today is first, it's about political redistricting. So I want to make sure we're all on the same page on what political redistricting is and how it works in the USA, because I know it's an international audience, and how mathematics is really playing a very interesting role in the legal debate right now. And then I'm going to talk about a specific technical problem that comes out of this redistricting challenge, which is sampling random partitions of a planar graph. And I'm going to focus on one specific algorithm called the Recom algorithm that's really become very popular and widely used in like independent redistricting commissions and even in litigation and court challenges. Then I'll focus on one of my recent papers with my advisor, which is a theorem about analyzing the properties of this algorithm and trying to explain it it's just a combinatorial structure theorem explaining the distribution that this algorithm samples from. And then finally, I will conclude with a list of many open questions. And I think the goal of this talk is to inspire some interest in these open questions, because this is I think a truly amazing area where mathematical theorems, totally pure mathematical theorems, are actually having a societal impact. And there's some very interesting technical questions that I hope to get some of you excited about to try to solve, because they really could have, they're cool, and they could have a cool impact on society as well. So please just interrupt me. I'm not good at seeing hand raises on my interface, so just interrupt me if you have any questions at all at any point. So, okay, political redistricting. So according to the United States Constitution, representatives in the House of Representatives shall be apportioned among the several states, each according to their respective populations, every 10 years. And the times, places, and manners of holding elections shall be prescribed in each state by the legislature thereof. So this is all the Constitution says about how we should select our Congress. And so in other words, every 10 years we have to take a census, and that determines how many seats in the legislature each state gets. But it's completely left up to the states how they want to fill those seats. And so what states do in practice is they divide their state up into geographic regions called districts, and each district then holds a separate election for one representative. And so this middle step of the state deciding how to partition their state and to fill the seats into the target number of districts is called redistricting. And this can have dramatic consequences for the partisan power in Congress after the election happens, because it's predictable how people are going to vote. And so you might try to manipulate this process. And this is known as gerrymandering. So in this little toy example, I'm plotting the same hypothetical state. Think of it as uniform population, and there's two parties, a red party, a blue party. And in each state, I have the same, in each figure, I have the same voting pattern, but I have different districtings. And so and each one gives a different balance of power between the blue party and the red party for those 4 representatives allotted to the state. So if you're the red party, you'd prefer this districting, and if you're the blue party, you'd prefer this districting. And so it's not surprising, given the political ramifications of this, that throughout history, politicians have tried to manipulate this process. Whoever's in power controlling the redistricting process can try to advantage their own party, and that's known as gerrymandering. A byproduct of gerrymandering is that it often creates very bizarre looking districts. In order to do this, you have to be very snaky, and in fact, that's where the term gets its name, is from a particular district that was drawn in 1812 in Massachusetts by the governor Elbridge Gerry, hard G, to advantage his own party. And it was said to look like a winged salamander, or Gerrymander, as this political cartoonist from 1812 put it. And so that's where the name comes from. And since 1812, gerrymandering is a persistent problem. This is a modern day gerrymander. This is a district based on the 2010 census drawn in North Carolina. And this was part of a map that was ultimately thrown out by a court as going too far for not just political reasons, but racial reasons as well. And so that's really kind of the only recourse that voting rights advocates have dealing with gerrymandered states right now is to take them to court and argue that the map is unconstitutional in some respect due to the gerrymandering that's going on. And so in these court cases, the fundamental question that comes up is, given a map, how can you tell if it's been intentionally gerrymandered? Did it come from someone just innocently drawing districts, trying to like preserve the like cities or counties and whatever units, or did it come from some scheming partisan that's specifically trying to benefit their own party? And the question of intent really matters here. It's not enough just to show that the outcome is unfair. To win a court case against gerrymandering, you have to prove that it was intentionally drawn to be unfair. And so how do you do that? And so this is where the mathematicians have a role to play, is you can do some statistical analysis on the data and say, okay, we're going to look at this partition with respect to data on how people are going to vote. And we can assign any map some sort of fairness score. Like, for example, like, if you have 60% of the statewide support for your party, they should win about 60% of the seats, something like that. Maybe you have some variations that take into account uncertainty over how people are going to vote, and you have some continuous spectrum of fairness on. And I don't want to talk about one specific metric of this, but you can define these fairness measures where you say, okay, fair would be like here, 0, 0, 0 on the spectrum, and this map receives a score of X, it's therefore not fair.
0 on the spectrum, and this map receives a score of X.
Some reverb from someone. Okay, it's been taken care of. But so this is how you could say that this map is unfair. But then the counter argument to this approach is that you might get pushback and say, no, it's not possible to be fair. This is an infeasible standard. You can't there's no way I could have drawn a map that meets the standard of fairness. And this is often like a valid complaint. Like, in the United States, Democrats are often, clustered closely together in cities. And if you're, doing natural looking partitions, trying to preserve cities, they're going to get packed together and they'll waste their advantage. Like things like that. There are natural geometric obstacles in the way of creating fair maps. So a more robust way of making this argument that it was really intentionally gerrymandered is to compare the plan to an ensemble of synthetic plans that you generate with some computer algorithm. And then you can plot some distribution over a histogram of how fair all of these plans in the ensemble are, and say, okay, yeah, maybe it wasn't possible to be fair given the geometric constraints we had, geographic constraints, but at least we should be somewhere here in the middle of this distribution, not way out here. And so you can say with some p-value that this map that was drawn that you're trying to throw out is an outlier in this distribution, and say therefore it was intentionally gerrymandered. And so this is a more robust argument that you can make, and this is often made in court cases all the time. This is becoming a standard technique to argue that something has been gerrymandered. But then the rejoinder to that is that how did you generate those random maps? This algorithm is somehow rigged up to draw this exact conclusion. And if I used a different map generation algorithm, it wouldn't look like an outlier anymore. Okay, so this is now the argument we have to refute. And this is what makes this a really interesting technical question, is that you're not just trying to design an algorithm to sample maps however you want, but actually having a way to explain the distribution matters. This is really crucial. Otherwise, you're going to be susceptible to these allegations of bias. And just to read an example from a recent court case to show that this does actually come up in courts. This is quoting from a 2017 Pennsylvania gerrymandering court case that eventually made it all the way up to the Supreme Court, where and this was rebutting one of these methods for the statistical analysis. The plaintiff's expert witness purports to have an algorithm that randomly generates maps. He has never evaluated this claim in any rigorous way. In my assessment of this random framework on algorithm on a very small toy redistricting data set, I found that the strategy generated a biased set of maps that oversamples some maps while undersampling others. Okay, so this was a mathematician called in as an expert witness to rebut this statistical approach. So how do we do this? How do we get this closed form? And that's the interesting question that I've been trying to tackle, and many other people have as well in computer science and mathematics. So from a theoretical perspective, the meta question, to just add a bit of notation to this, is we're given some planar graph G of census blocks, or maybe counties, precincts, whatever. There are these indivisible units of redistricting based on the census that you can't further subdivide. Okay, so you have to, so it's really like a graph partitioning problem rather than some more abstract geometric problem. That's the most realistic way of modeling this. So you're given some number M also, which is the desired number of districts. And this is based on the apportionment. Each state is assigned how many districts do you need to form. So redistricting is the act of partitioning the vertex set into equal sized districts, inducing connected subgraphs. And so I'm making a bunch of simplifications here. In this little toy picture, I'm assuming that all of the, that first of all, we want to have exactly balanced partitions, and so also that all of the census blocks have equal population. In reality, you have some epsilon slack maybe, and you have you have different weights, population weights ascribed to each of these indivisible units. But I'm not going to go into any of those details. I'm going to sweep that under the rug. Yes, Patrick.
That districts are connected. Is that just part of your model as a simplification, or does this
That's
have to
a
be...
legal requirement.
Okay.
Yeah.
Thanks.
And in the case of like islands and rivers, things are considered legally adjacent. And so yeah, you add those edges to the graph. Yeah, you always need connected districts, and that's what makes this problem very hard. Yeah, the balance constraints and the connectivity constraints do not play well with each other.
So here, equal size means the areas are equal, something like that. What do you mean?
The population weight. So
okay,
I think of this.
Okay.
Yeah, and then I'm going to think of them as unweighted. So the same number of vertices in each component, in each district.
Okay.
Yeah, good question. So yeah, that's the simplifications I'm making for today's purposes. So the big theoretical question in this field, at least from my perspective, that is still somewhat open, is to find an algorithm that on real world instances, so everything in red here is something that should be made more formal. It's a sort of, that's why it's a meta question, is that it should run in polynomial time. It should sample at least approximately from some distribution which we can explicitly describe with a closed form. So this is this is the key explainability constraint. And thirdly, it should be a nice distribution. It shouldn't be districts that look like no human would ever draw them, like really snaky, horrible looking districts. It should favor natural looking partitions. And this is a very meta constraint as well. And so this is like, if we can come up with more algorithms for that, I think this is a very useful exercise that people should be working on. And I will talk about one great algorithm that seems to satisfy these properties very well. And that's the Recom sampling algorithm. And that's going to be talking about for most of the talk. But before I do that, I want to briefly mention like the other end of lower bounds of what are the impossibility results that are known. Are there some distributions that you can't sample from approximately in polynomial time? Okay. So because if we drop the polynomial time constraint, this is easy. You can enumerate all possible partitions, do whatever analysis you want, and then just spit out a sample with whatever probabilities in any closed form you want. But doing this efficiently is very tricky, it turns out. So I just want to briefly mention lower bounds. There's basically one paper that has been published on lower bounds. And the results are pretty weak. And to state them, of course, it's going to need some complexity theoretic assumptions because we don't know how to say things that aren't doable in polynomial time unconditionally. So I just because I know that not all of you are computer scientists, just a brief recap on what the assumptions you need for the impossibility results are. So the class RP, it's a complexity class. It's a class of decision problems solvable by a polynomial time randomized algorithm with bounded error and perfect soundness. So what that means is it's some efficient algorithm, polynomial time, that if the answer is yes, the algorithm should say yes with probability bounded away from 0, so like greater than 1/2. And if the answer is no, the algorithm should never say yes. Okay, so that's what the perfect soundness means. So we think that, so we know that P is a subset of RP and RP is a subset of NP. And the conjecture is that RP is equal to P, but is a proper subset of NP. Okay, so if RP was NP, that would be a big surprise. And the lower bounds on this approximate sampling take as an assumption that RP is different from NP. So just to briefly summarize, here's like what I think are the biggest results from this paper by Knight, DeFord, and Solomon showing lower bounds on the sampling problem, is that unless NP equals RP, here are some distributions that we can't approximately sample from in polynomial time. Okay, so first, unbalanced partition. So I dropped the constraint that they have the same number of vertices in each partition of a given planar graph uniformly at random from the set of all unbalanced partitions of a planar graph.
Sorry,
Okay, but
M
this is
is the
still
number.
connected.
M is the number of parts.
Yes,
Okay,
no,
thank
good
you.
question. Yes, and M throughout this talk is the number of districts. And so these are like things that are even hard, even for just partitioning a state into 2 districts. And all these are, connected districts for all these cases. So that's interesting to know. And they also, but we really care about the problem of sampling balanced partitions, and is that still hard? So yes, there is a result on that as well. If I require epsilon balanced partitions, and in fact, it's even hard when I restrict the input census block graph to be 2 connected and planar. This is just a slightly stronger. And again, uniformly random from the set of all partitions. So that's another thing we can't approximately sample from polynomial time unless NP equals RP. And then there's a few others as well, just to make it even more realistic. It's not just always a connected planar graph, but it's in fact often 3 connected, and there's some bound on the degree and some bound on the dual degree of the graph. And so even on those instances, this problem is still hard to sample from unless NP equals RP. But then we have to drop balance constraint again. And then finally, there's one more result, which I just mentioned because it's kind of similar to a result I'm going to be stating for my own paper later, is that you can't sample from the following distribution. So it's not uniformly over all partitions, but you weight them proportional to some constant to the number of cut edges of the partition. So a cut edge is an edge that has its endpoints in 2 different districts. And so when you have a partition with few cut edges, because lambda is less than 1, that means it's going to be more likely to be sampled. So this is like a nice distribution you might want to sample from, because it incentivizes like more compact looking partitions with fewer cut edges. The ones with many cut edges should have less probability. So this is a nice natural distribution you might want to sample from. And this is again something that you can't do in the worst case. And so how all these reductions go, they're all based on the same idea, the basic same idea, which is to reduce from the Hamiltonian cycle problem. So say you want to solve, say you want given a graph and you want to figure out if it has a Hamiltonian cycle. So what you can do is you can take every edge in the graph and replace it by this chain of little 2 cycles. And then, so suppose you had some algorithm that could sample cycles, not partitions, but cycles from this graph, uniformly at random from the set of all cycles. Well, if you do this with enough of these little loops on each edge, then you can see that most of the cycles in the graph are following the Hamiltonian cycle of the original graph you started with. So so you have like exponential weight put on these cycles. And so if you were able to sample uniformly at random from the set of cycles of the new graph you've constructed with these gadgets put in, then you could effectively solve the Hamiltonian cycle problem in polynomial time. And so that shows that unless NP equals RP, you can't sample cycles uniformly in polynomial time. But what we really care about is sampling partitions. And for that, you just use duality. Sampling a cycle of a planar graph is the same as sampling a partition of its dual. So variants on that idea with multiple districts too are achievable as well. And so that's the main idea behind all of these reductions is via the cycle sampling problem via Hamiltonian cycle. So there's many limitations to this approach. The results are kind of weak. I mean, a big one is that there's only this one result in the whole paper where it considers the epsilon balanced partitions. That's what we really care about. And that result is kind of standalone and holds only for m equals 2. So that's kind of weak. Also, the notion of approximate sampling is really stringent. It's that there should be a very small total variation distance between the distribution output by the algorithm that's sampling from and the target distribution. So it's saying that, yes, it's not possible in polynomial time to do this really precise approximate sampling, but maybe there's some relaxation that you could do that's practically meaningful. And the biggest problem of all, though, is that these instances are not real world instances. So imagine taking an arbitrary graph on which Hamiltonian cycle is a hard problem and then doing this construction, making a bunch of 2 cycles. That is not what real census block graphs look like in practice. And that's all that it's shown to be hard on, essentially. So it's, we really care about average case hardness here. This theorem only says in the worst case that you can't do this in polynomial time. So I just want to put that out there as that's sort of the opposite end. Very little is known in terms of lower bounds. And so that's also an interesting question to try to improve these. Any questions on that stuff? And we'll go to the Recom algorithm now. Okay, so as I said, there's this awesome algorithm, and it's becoming sort of the state of the art. And it's being used currently, like today, by independent commissions and in these litigations, because it seems to satisfy those three properties pretty well. So how it works is it's an MC-MC algorithm. It's going to take a walk on a Markov chain. So you start from some arbitrary partition of the state into connected subgraphs of equal size. Generate that however you want. Okay, use some algorithm. It's not hard to come up with a solution for typical census block graphs. Then we're going to repeatedly get new partitions via the following step. Okay, so this is the transition function. We're going to randomly merge two adjacent districts, D1, D2. Okay, so in this diagram, say I merge these two into one bigger district. Then we're going to sample a random spanning tree on this merged district. Okay, so that's just this tree here I've highlighted. This is the tree we happen to sample. Then we're going to look at that tree and see if there's a single edge that I can remove from it that will split it into two subtrees of the same number of vertices, or approximately same number of vertices in a more realistic version. And this is not guaranteed to exist. And if it doesn't exist, I have to start the whole thing over again. But if it does, then I say, okay, we're going to cut it there. And those become our two new subgraphs. Those two subtrees induce a new partition into districts. So I've just merged two adjacent districts and found a new way to split them by sampling a random spanning tree. And so we just do this over and over, run for many, many steps, and then output the final partition and call that our sample. And you can even do this. You don't have to like rerun this for each sample and ensemble. A nice property of this is after it's, if you let it run for a while, so that the initial partition doesn't matter, then you get a bunch of samples just by taking consecutive steps from this Markov chain. That seems to give you really nice ensembles as well. Okay, and any questions on how the Recom algorithm works?
So what is, how do you choose two districts in the first step?
Just randomly. Any two adjacent districts.
Okay, so is it a uniform distribution on the pairs of adjacent districts, or you choose the first one randomly and then you choose the second one randomly among the other ones which are adjacent?
So I don't know the details, because to actually get the theoretical properties, there actually is like a technical thing you have to do for this step. And so I don't exactly recall how you do it. Yeah, I can point you to a paper that will talk about the version of this algorithm that actually has theoretical guarantees and how you do that step.
Okay, thanks.
Sorry.
So
oh, sorry. Yes.
Another small question. I mean, maybe you were getting to that, but can every possible partition be reached this way? Big question. Yes, save that for later. Okay.
I'm not. Yeah, this is still from a theoretical perspective. Yeah, that this is a big open question. Surprisingly, even on very tame graphs like grid graphs. Yeah, it's kind of ridiculous that this is an open question still, but it's a very hard question. Yeah. Okay. So does it satisfy those properties I claimed? Firstly, does it run in polynomial time? Empirically, I'll say the answer is a hard yes. This is an efficient algorithm. It's very practical for real redistricting graphs. It seems to run in polynomial time. From a theoretical perspective, again, that's one of my open questions. I'll come back to that at the end of this talk. Does it sample approximately from a distribution that you can explicitly describe? So this is really where Recom is an awesome algorithm. So it's been shown that if you do some slight tweaks, which I don't want to get into, of the transition function, you can get it to exactly target the following distribution. This is the stationary distribution of the Markov chain, is called the spanning tree distribution, where the probability of sampling some partition D1 through DM is the product over all the districts of the number of spanning trees in that district. Okay, so it's a closed form, right? You're not trying to bias one party over the other. It's like, this is literally what Recom is doing. So that's why this algorithm is so great, is because it not only runs efficiently, but you can explicitly describe the distribution in terms other than the distribution that the algorithm samples from. You can always describe a distribution that way, but this is like a real closed form for exactly given a partition. I can quickly see exactly, what is the probability that that partition would be sampled, or at least proportional to. Yeah. Okay. So Is the jury convinced by this explanation, though, that this is it's still a little like non-transparent, right? You have to know what a spanning tree is. You have to explain that to the jury in this court case, probably. But there's reason to believe that it is a nice distribution to sample from, and so the property that we really want is that this favors natural looking partitions, and you can convince yourself by drawing a bunch of small examples that this is a good distribution. So for taking this little running example toy graph here, I'm considering two possible partitions here on the left and on the right. The one on the left is pretty snaky. Every district is itself a tree, and there's a bunch of cut edges. All the ones in red are the cut edges here. So it's not very compact. And what is the spanning tree score, which is this product of the number of spanning trees? It's 1. Each district has only one spanning tree. So this is sampled with probability proportional to 1. Whereas the partition on the right is a lot more compact, much fewer cut edges. And here the probability of sampling this one is proportional to 192. That's 8 times 3 times 8 is the spanning tree score for this partition. So this partition on the right is a lot more compact than the one on the left, and it's 192 times more likely to be sampled from Recom's stationary distribution. Okay, so based on examples like this, you can convince yourself that this is probably a good idea to sample from the spanning tree distribution. It's favoring partitions that look more compact, having fewer cut edges. Okay, and it's intuitive, right? The more edges you delete, the less spanning trees there's going to be in the product. And so one of my this recent paper that I'm going to be talking more about in depth was making this explicit for the first time. So this is the theorem from a paper from Soda this last year, which is that over any class of planar graphs where the second highest degrees of G and its dual are bounded. So that's what I take to be our model of what does a realistic census block graph look like. And I'll talk about why second highest degree appears in a moment. This is the conclusion. The relative likelihood of sampling some partition P versus some other partition P prime is inversely exponential in the ratio of cut edges of P to the cut edges of P prime. So in other words, if P prime has way more cut edges than P does, then P prime is going to be much less likely to be sampled. Okay. That's what it's saying. So in other words, and it's because you see here, P prime is in the denominator here and P prime is in the numerator here. So it's inversely exponential. Right. So in other words, the spanning tree distribution from which Recom samples is the main thing it's doing is roughly weighting partitions by their compactness. Okay, and there's a bunch of constant factors that are hidden here. It's much coarser notion of approximate sampling than total variation distance for sure. But it's a nice theorem that says it's trying to explain the spanning tree distribution and in terms of compactness, showing that yes, it does favor natural looking partitions. So a few remarks about this theorem. Firstly, why the second highest? Well, if I said first highest, this theorem wouldn't be very practical. Why? Because you can think about an actual census block graph. Its dual consists of the outer face, remember, and so the outer face we should allow that to have unbounded degree. And so if I require the outer face to have bounded degree, then this wouldn't be a very practical theorem. It wouldn't apply to like real census block graphs that you need to redistrict in practice. On the other hand, so first highest would be a kind of a useless. On the other hand, if I said third highest, then the theorem wouldn't be true. We have some explicit counterexamples both for the primal and the dual. This is the one for the dual, where I've got this graph. It's a family of graphs with a really large cycle in it. So I've got two regions in the dual that have high degree, many edges around this region and around the outer face as well. So it's not bound. The third highest degree is bounded, but the second highest degree is not bounded of the dual graph. And you can show that this theorem breaks down for this infinite sequence of partitions defined by the blue one and the red one. I won't go into more detail about that. So that's why the second highest is really a tight statement in that sense. And I'll also say that this is the sort of asymptotic version of the theorem. We also have like an explicit version with exact bounds on relative likelihoods of sampling partitions. So for example, our theorem implies that on sufficiently large grids, a partition with 7.23 times as many cut edges as another partition is less likely to be sampled from the stationary distribution, the spanning tree distribution. Okay, so and you can read the paper if you're interested in that. And I will talk a little bit about the proof now. But any questions before I go into the proof sketch of what this theorem means and anything about it?
So is the theorem still true for the highest degree, even if it might not be useful?
Oh yeah, I mean that's a weaker statement. Yeah, over any class where the first degree is
bounded. Yeah,
bounded.
sorry,
Yeah.
sorry. Yeah, fair enough.
Yeah. Okay, so how do we prove this? Okay, so I'm going to take this running example of partitioning a grid graph, a 6x6 grid graph into 3 pieces. So we want some sort of bounds on the probability of sampling a partition in terms of the number of cut edges. That's the main objective here. And so how are we going to compute the probability of sampling this partition from the spanning tree distribution? Well, that's exactly the same as I'm going to connect the districts up by just adding m-1 edges. And the probability of sampling the original partition is the same as the number of spanning trees of this graph, right? It's the product of the number of spanning trees in each of the 3 components. Okay, so now we have a single grid subgraph, and we want to count the number of spanning trees that it has. And so so that's proportional to the probability that if I take a random spanning tree of the entire grid graph as a whole, then it doesn't contain any of the cut edges that aren't in this partition. Okay, it's exactly the same thing. I'm just adding a normalization term that's for the total number of spanning trees in the whole graph. So this is what we want to compute. We want to bound the probability of that a random spanning tree does not contain any of the cut edges, so any of these red dashed lines, as some function of the number of cut edges. Okay, and this seems intuitive that such a relationship should exist. The more cut edges you have, the more you're adding more constraints on what the random spanning tree should not include in it, and so it should be less likely to be sampled. Okay, so it's kind of intuitive that some relationship should exist. And you might think, oh, maybe we can just apply standard bounds from combinatorics literature on number of spanning trees in terms of number of edges to just settle this question immediately. But it turns out that those sorts of bounds don't work because you have a lot of error term. You have a huge error term coming from the total number of edges that aren't cut edges. So we really need to look in these marginal probabilities where only a very small fraction of the edges are cut edges. Otherwise, these bounds from the literature on counting spanning trees based on number of edges and degree bounds, that doesn't really help you very much. Okay, so how do we do this? How do we compute the probability that a random spanning tree of the whole grid graph does not contain any of these cut edges? Well, I'm going to define pi. I'm going to imagine iteratively deleting each one of these edges one by one. And at each step, I'm going to let pi be the probability that the ith deleted edge is not contained in a random spanning tree at the time that I'm deleting that edge. Okay, so what the probability that a random spanning tree does not contain any of these edges is then just the product of all these pi values. Okay, I'm just going to keep looking at the marginal probabilities one by one as I delete them. So we're done if we can prove the following lemma, is that the product of these p values as I go delete these edges, remember each pi is the probability that a random spanning tree of the whole grid graph does not contain the given cut edge I'm deleting on step I. We just want to show that the geometric mean is bounded away from 0 and 1. So in other words, there exist constants C1 and C2 strictly between 0 and 1. And these are going to have to depend on the bounds we assume on the second highest degrees of G in the stool, such that for any sequence of T deletions, of whatever the cut edges I'm going to delete are, the product of all these P values is bounded between C1 to the T and C2 to the T. So why does this imply our theorem? Before I say that, I'll just say that we do have a more general version of this lemma where I'm not just doing deletions, but also contractions. And this we feel might be of independent interest as well. It's just a complete dual version of this lemma that handles both deletions and contractions. But okay, so how does this lemma imply the main theorem? Well, what do I care about? The probability of sampling some partition P versus some partition P prime. Well, I do this analysis with the P values are when I'm deleting the cut edges of P, and the P prime values are the probabilities for when I'm deleting the cut edges of P prime. So this equality holds. This is just I have the same normalization term in both cases. And then I apply this lemma, applying the applying the lower bound on the numerator and the upper bound on the denominator. And then what's t in this case? Well, t is the number of cut edges minus m minus 1. Remember, I had to add m minus 1 edges to connect all the districts up into one graph, but that's just a small constant term that kind of comes out in the big O analysis. What is this? And basically you stare at this and you see, yes, it is the form that I claimed it is. Because the C1 and C2 are less than 1, we flip and the p prime in the denominator comes up to the numerator. So this really is inversely exponential in p over the number of cut edges of p over the number of cut edges of p prime. Okay, so this is a simple derivation, and you follow the math. This works out. So all we got to do is prove this. The geometric mean of these p values is bounded away from 0 and bounded away from 1 by constants. And so just recall, I'm just putting the definition up again. PI here is the probability that the ith deleted edge is not in a random spanning tree of the graph when I delete that edge. Okay, so I'm going to define Ri to be 1 minus PI. In other words, the probability that the ith deleted edge is in a random spanning tree. So I'm sure many of you in the audience are familiar with an alternative interpretation of what Ri is. And why I use the letter R here is that if I replace the graph with a network of 1 ohm resistors, and then I ask what's the effective resistance across an edge, from like I hook my electrodes up, one of them up to one vertex and another up to the vertex across that edge. The effective resistance that I'll measure across that edge is exactly this Ri value. The probability Ri is equal to the effective resistance across the ith deleted edge when all edges are replaced by unit resistors. Okay, so very, very cool theorem from spectral graph theory, and it just gives us a nice way to more easily reason about giving bounds on these RIs, which then give us bounds on the PIs that we need. And so I don't want to go into any more details than necessary, but what this lemma implies from the effective resistance standpoint, it's easy to see the following conclusions: that if the ith deleted edge is adjacent to a vertex of degree k, it has effective resistance at least 1 over k. Okay, and so that you can just use the effective resistance, basic laws of how electrical resistance works, and to easily derive this conclusion. There might be another way without doing effective resistance as well, but this makes the reasoning very, very simple to see this lemma. And so why is this nice? Is that, well, if the second largest degree of the graph is at most k, then so why second largest here? What do I know about that edge? Is that one of its endpoints might have high degree, it might have be the largest degree in the primal graph, but the other endpoint should be bounded then by the second largest degree. So I can at least apply this bound to one of the endpoints of this edge. So that's why I'm allowed to relax this, and I don't need to require that the first largest degree is bounded just the second largest degree of the graph. But essentially using this lemma, I can upper bound PI by 1 minus 1 over k. Okay, so this is great. We're done. Every PI is bounded by 1 minus 1 over k. So if I just set C2 to be 1 minus 1 over k, that works. Okay, I didn't even have to, on every iteration, each PI value is less than 1 minus 1 over k. So if I take a product of t of them, it's less than that raised to the t power. Okay, so that was the easy direction. That's great. And then can we apply the dual version of this as well? Is that if the ith edge is in a cycle of length k, it has effective resistance at most 1 minus 1 over k. Okay, it's a complete dual to this other lemma. If you go through the calculations, that's what you'll see, and it's easy to prove using the effective resistance formulation. And I don't want to go further into that. But so then can we do the same thing and then get a lower bound on the PIs? Well, same idea then. If the edge, so we take our edge, we want a lower bound we want upper bound on its effective resistance, so we get a lower bound on the probability it's not contained in a random tree. And we say, well, we have some bound on the second largest dual degree. It might be, but one of the regions might be that outer face, which has high degree, but the other region will at least have will have small degree in the dual graph, a small number of vertices. So if the second largest dual degree is at most k, then I can use that region to bound the effective resistance and get the following lower bound that PI is greater than or equal to 1 over k. So it looks like we're great again, right? This is bounded away from 0 if k is a constant. But the catch here is that this holds at the beginning, but recall that I need to do this not in the original graph I started from, but in the graph obtained by after I've deleted a bunch of edges already. And so that's the tricky part, is that if some edges have already been deleted, then I'm not able to claim that the edge is next to a graph with small dual degree. Okay, excuse me. Sorry, someone just came in the room. And so, yeah. And so this is what causes us trouble. And in fact, these PIs, there is no lower bound on every PI value. They can get arbitrarily small. So I need to argue that in an amortized sense, they don't get arbitrarily small. The average does not get arbitrarily close to 0. And so well, I'm not going to be able to get C1 equals 1 over K, but I claim that C1 equals 1 over 2K will work. And if I amortize the really small p-values over previous iterations where the p-values were not so small. Okay, so how do I do that? Oh no, first let me show you an example of this happening. So in this running example, the graph is a grid graph, so K is 4. The bound on the vertex degrees and dual are both 4. So I'm claiming for the lower bound, which is the hard part here, is that on average, these PI values, the probability that each cut edge is not contained in a random tree of the graph is greater than or equal to 1 over 2 times 4, so 1/8. And so I've gone and actually computed what these p-values are. So let's say I'm going to delete them in this order. I'm going to start like top to bottom, left to right. So I'm going to delete this edge, then this edge, and this edge. And I'm going to see what is the probability that that edge is not contained in a random tree. So the first one happens to be 0.44. Okay, that's the probability that that edge was not contained in a random spanning tree of the graph. Okay, the next one is 0.40. So yeah, these are going, you'll notice these are going to start getting smaller. And the worry is that I want to show that they don't get too close to 0. All I care about is that on average, these on geometric mean of these is greater than 1/8. And so clearly we're good so far. But as I delete them, they're going to get smaller and smaller and smaller. And so the probability this edge was not contained in any in a randoms tree was 0.34, but still doesn't look like they're getting close to 1/8. But now this is the one that's going to cause us trouble here. If you look at the structure of the graph I currently have now, after I've deleted all these edges in this channel here, this edge is a pretty critical graph. So it seems very likely that it should be contained in a random tree. And so in fact, the probability that this edge is not contained in a random spanning tree of the current graph is going to be very small. It's going to be 0.11. And the thing about 0.11 is it's less than 1/8. So this bound of 1/8 does not hold at every iteration, but I want to claim that it does hold on average because I had a bunch of previous iterations to get to that large cycle that caused this trouble. And so I want to say if I average this with all the previous iterations, yes, it will be better than 1/8. So the way I'm going to formally prove that is I'm going to define the following potential function. So I'm going to imagine placing a stack of pebbles in a bunch of regions. So in the outer region, or whatever the region is that had the unbounded high degree, I'm going to put a stack of pebbles equal to the degree of that region. And then I'm going to put one pebble in every other region. So I'm defining the potential function pi to be the product over all the regions of the number of pebbles in that region after I delete the first I edges. So whatever the graph looks like, and when I delete an edge, I'm going to merge those piles of pebbles and consider them part of the same region now. So the key claim then is that on each iteration, I want to say pi is greater than or equal to 1 over 2k. That's our objective. And I don't have that at every iteration, but I do have that it's greater than 1 over 2k times pi divided by pi minus 1. So whenever I have these bad iterations, I want to claim that there's a drop in the potential function that lets me still claim this holds. And so then it's easy to see that this implies that the lower bound that we needed for the lemma, because if I multiply all these pi's together, I just get a 1 over 2k to the t term and times a telescoping product of these potential functions. And if I cancel, I'm left with 1 over 2k to the t times pt over p0. And then you just have to observe that the potential function can only increase. PT, because I've always got this region, the initial value of the potential function is just degree of R naught, and those pebbles are always going to be together in the same pile. They can't be split up. So you're never going to lower than the value of PT is at least the value of P0. So this is indeed greater than or equal to 1 over 2k to the t. So I hope this will become clear on the next slide. So this is going through this example with this potential function. So again, I put a stack of 20 pebbles on the outer face because there's 20 edges on the outer face, and then 1 pebble in each of the other regions. So our initial value of the potential function is 20. It's 1 times 1 times 1 times 1 times blah, blah, blah times 20. So there's 20 and a bunch of ones, and I just multiply them all together. And so as we delete edges, okay, so again, this is the same p-value as from before. And I want to show that each p-value is greater than or equal to 1/8 times the ratio of pi over pi minus 1. And since the potential function is increasing, we're still good, because this pi is greater than 1/8, pi times 40 over 20 is also going to be greater than 1/8. So we're still good. And so why is it 40 here? These two pebbles merged into one pile. So instead of 1 times 1 times 20, it's now 2 times 20, which is 40. So I keep doing this again. I get the same p-values, again, increasing the potential functions. I add to this stack here. It's just going to multiply. I'm going to add 20 each time. And so I keep going, keep going, keep going. Potential functions increasing, increasing, increasing. And then we get to this point, which is where things started to go wrong last time. And now watch how they're going to be okay, is that I've got a very high value for the potential function. I've got 20 times 7. And that allows me to take, so when I delete this edge, however, instead of being 20 times 7, these piles are going to get merged. And so now it will be 20 plus 7, so 27. So while it was not true that 0.11 was greater than or equal to 1/8, because I had this huge drop in potential function, it is true that 0.11 is greater than 1/8 times 27 over 140. So this potential function essentially takes care of the fact that, when I've got a high potential function, high value of the potential function, it means that I've taken a bunch of iterations with higher p-values, and this is exactly how I cancel that out then. And this is the main idea for why this works. And any questions on the proof? That's all I'll say about the proof. I'll just wrap up now. Okay, so just to recap, the main point of this theorem was a theoretical confirmation that Recom does favor compact maps, justifying why this is a good algorithm to use in these redistricting court battles, or also by if an independent commission wanted to use this for part of their work too. It's a good distribution sample from
planar graphs. I mean, in principle, you can use similar Markov chain Monte Carlo methods for all kinds of graphs.
Yes. So I mean, our theorem only holds for planar graphs, and all census block graphs are planar. Okay, there's maybe some weird contradictions with islands. I'm not sure. I think they're planar or almost planar for sure. Yeah. But
I mean, the methods that they use, you can define these Markov chain methods probably for general graphs rather easily. But the method here you use is really planar. But
yes.
So with the theorem, do you know that the theorem is only planar?
I wonder. Yeah, I hadn't thought about that. I wonder if there's because all you need for this theorem to be true is some sort of bounds. Like I bet if you did a planar embedding, you could do something similar. I haven't thought about whether this generalizes to non-planar graphs. It's a very interesting question. Yeah, I'll think about that and get back to you. Yeah. So I just want to end by listing a bunch of concrete open questions. I had the meta question earlier, which is I think the really big question in this field is what can we sample from polynomial time? But here are some more like concrete questions of things we don't know how to prove, even on grid graphs. Okay, so these seem like they should be easy, but they're trickier than you think. So the first question is what has been called the isospanometric conjecture, is that among all subgraphs of grid graphs with exactly n squared vertices, the square grid graph of n squared vertices has the most spanning trees. So this is very similar in spirit to our theorem. It's kind of an extreme version of that. Our theorem is saying that the more compact you are, the fewer cut edges, the more likely, the higher your number of spanning trees are. And this is kind of the extreme point of that. The very most compact district of all is one that's a square, and that should have the very most spanning trees. Okay, so yeah, this is still an open question as far as I know. No one's been able to prove this yet. Second is we'd really like to know if, from, like, as I said, Recom is a nice algorithm, but and it's very efficient in practice, but it would be nice to know that it's theoretically a polynomial time algorithm. And you know, one of the things that we need to prove is mixing. But even before that, like even the transition function is on shaky ground here. And that is not even obvious that the transition function runs in polynomial time. And that's because you might have to run it many attempts until you get a tree that actually splits into two subgroup trees of equal size. This is not, there's not going to be necessarily one edge that you can remove that will split it into subtrees of equal size. So to show that the transition function is really a polynomial time algorithm, you'd have to lower bound the probability that if I sample some spanning tree of, say, a grid subgraph for the grid version of this, that it can be split into almost balanced subtrees. You want to bound that as something like 1 over polynomial function of that. And this is yeah, I've thought about this problem. I'm not sure how many other people have thought about this, but it seems to not be quite so easy to show this. But then even if you can show that the transition function is polynomial time, then the big question is, does it mix in polynomial time? And so this is really I think the huge question for Recom is that can you show rapid mixing? And I know there's been some recent results in the theory CS community lately about new techniques to show rapid mixing. But before you get too excited to use those ideas, as some of my collaborators here at Harvard one time did, I should warn you that there's a really more basic thing that needs sorting out first before you can even attempt to prove rapid mixing, is that showing that the state space is connected. Clearly, this is a necessary condition for it to mix in polynomial time, is that it's possible to get from any partition to any other partition via a series of Recom moves. This has been open for decades. It's been proved in various weaker forms like you dropping the balance constraint. You can prove this and by some older works. Yeah, the question of can you do this with a balanced or approximately balanced districts at every step is still open. And so I do want to say a few words about this, because I think this is one of the most interesting open questions, and it's definitely been around for a very long time, even before this sort of redistricting paradigm came about. This was an open question, and so I want to say a few more words about this. Formally, this is the problem, and what's known about it is, so n is the side length of the grid, m is the number of districts. So I want to know for which n and m is it possible to transition between any two partitions of an n by n grid graph into m balanced connected subgraphs. And here I'd say exactly balanced. Okay, every step. So m has to be divisor of n times n, if this is going to be even well defined. And at every step, I'm merging and splitting adjacent subgraphs, and I'm preserving balance and connectivity constraints at every intermediate partition. Okay, so this is the Recom state space connected when I impose hard balance constraints, even on grid graphs, square grid graphs. And this is the big question. So I'll say what's known for some small values is very little. For m equals 2, this is trivial. Why? Because if there's two partitions, everything is connected. The state space of Recom is a click. You can go in one move from any partition to any other partition. Okay, so there's nothing really to prove there. So that's basically all we know. For m greater than or equal to 3, this question is open. And it's like even on square grid graphs, and it's kind of amazing, right? That this is open. So you take some sufficiently large grid graph, n by n grid graph, where n is the multiple of 3, and look at the partitions into 3 subgraphs of equal size, and say, can you go from any one to any other by iteratively merging and splitting pairs of those 3 districts. So each step, you're allowed to repartition 2/3 of the entire graph any way you want, as long as it's connected partitions in the end. And so it seems like this should, obviously be doable. But yeah, several people have worked on this. This question is still open, even for m equals 3 for large grid graphs. An alternative way you can try to attack this problem is instead of looking at a small number of districts, you can look at a small district size. Okay, so here the district size is n squared over m, and you can look at what happens when that's small. Oh, sorry. Before I go into that, I'll say yeah, I forgot this recent result. This was proved on a triangular grids, so like a different grid mesh. When the whole graph is like a triangle, and every vertex is degree 6. So this was proved to be true on triangular grids just for the case of m equals 3. This is a recent, so far unpublished result. I expect it'll probably be on the archive in a couple months maybe. Yeah, so this is just to show that people are thinking about this. It's still an open question. That this grid mesh is nicer because every vertex is, if you look at its neighbors, they form a cycle. That's not true on grids. And so Sarah, when I went to this talk, she said that that's probably the main thing that she used in proving this theorem, and it probably could generalize to arbitrary graphs with that property. But who knows? For grids, still an open question, even for m equals 3. Okay, so fixing the district size now, I'll say what's known for that. So n squared over m, this is the number of vertices per district. So this is when this is 2, this is domino tilings. Okay, so can you go from any domino tiling of a grid graph to any other one by iteratively, taking side-by-side dominoes, and if they're vertical, then you make them horizontal. If they're horizontal, you make them vertical. That's the only Recom move you can use in this setting on grid graphs. And you can show via a not too hard exercise that the state space is connected for a domino tilings. And this is like, it's a kind of famous puzzle, right? If you like, can you make a domino tiling where no 2 dominoes lie exactly adjacent to each other? It's a fun puzzle showing that no, you can't, and you can extend that proof to show that actually, yeah, the Recom state space is connected for domino tilings. It's not too hard to show. Okay, what about 3 ominoes? So here, actually, surprisingly, the answer is false. So you can have locked partitions. In other words, partition of a 6x6 grid graph into 3 ominoes such that no pair of adjacent 3 ominoes can be repartitioned into a different shape. So you can just tell from looking at this that yeah, there's no 2 adjacent 3 ominoes that you can repartition into a different shape. And the nice thing about this particular counterexample is that you can tile it with itself to get n arbitrarily multiples of 6, because if you tile this with itself and flip every other one, it preserves this property that you can look across the boundaries of these cells that yeah, you can't repartition these along the boundary either into different shapes, preserving connectivity and balance constraints. Okay, and then for 4 ominoes and higher, again, a completely open question. I've worked on this quite a bit, and one of the and I would conjecture that the state space is connected for 4 ominoes on grids, but a big obstacle is that you have to use the boundary of the grid somehow. And what do I mean by that is that we can come up with similar examples like this, isolated points in the state space on toruses. Okay, and in fact, for even arbitrarily large polyomino sizes, I've been able to construct counterexamples on toruses. So really, to prove this state space connectivity conjecture, you have to use the fact that the grid has edges and corners. And so I'll show you an example of what I mean by these locked torus partitions here. So this is on the left. This is for 4 ominoes. This is a periodic infinite 4 omino tiling, or torus tiling, if you will, where you can't repartition any pair of 4 ominoes in a different way. And then on the right, this is a similar thing for 5 ominoes. And this construction on the right actually generalizes to an infinite family of omino sizes, polyomino sizes that makes locked partitions of a grid. So yeah, the state space is disconnected on toruses for arbitrarily large polyomino sizes given sufficiently large grids. But what we really care about is grids. That's like, and that's not just me that cares about this. There's the literature on this problem really uses grids as like a nice example of the problem that we should try to tackle first, because it's a very good model of actual real life census block graphs in many ways. So that's all I have to say. I'm happy to take any questions. I'll put the list of open questions on the slide, and yeah, thank you.
Great, thank you very much for the talk. Are there any questions?
I have a question. So if we know that the state space is not connected in some cases, and it's possible that it is not connected in more general cases, then doesn't it mean that for this Recom algorithm to be fair, it is important from which state it starts?
Yeah, and so that's the concern, right? And that's why this is really a really important open question that we should try to solve. And I mean, the answer, like everyone that seriously is working on this thinks for real life census block graphs, the answer is like obviously yes, especially with the epsilon balance constraints. The state space should be connected. And not only that, but the mixing for Recom empirically seems to mix in polynomial time, like really, really fast. Like it takes for actual like scale instances, after 2000 iterations of the transition function, your partition looks completely different than whatever you started with. And it seems like you're getting a sample from the stationary distribution. So like, yeah, from an empirical perspective, this isn't a really big issue. Like everyone believes empirically that this does mix in polynomial time. This does mix very rapidly. But yeah, from a theoretical perspective, that is the worry. And so it would be great to rule that out. It would be a nice strong justification that Recom is a good algorithm to use for this purpose.
And another question. So you are talking about real life examples. So what is the size of real life graphs? So how many vertices do they usually have?
Oh shoot, I don't know the number off the top of my head.
At least, is it like 10 or is it 100?
Oh no, wait, like the number of census blocks in a real life graph?
Yes.
Oh no, in much higher orders of magnitude. The smallest one is 99, which is the state of Iowa, and because they use counties as their indivisible units, and no other state uses counties as their indivisible units of redistricting. So the census blocks are really small. You have like tens of thousands of these. I hope that's the right order of magnitude. Okay. I might be off on that. Yeah.
Thanks.
All right, are there any other questions? So I have a small one. So you mentioned that it's now known for triangular grids. And that kind of one of the reasons why things work there is because every neighborhood is a cycle. Right? So, I mean, that is true for any maximal planar graph. So would these methods maybe extend to maximal planar graphs, or is it? Really
yeah, this isn't my result.
Okay.
But yeah, she thinks that probably yes. I mean, it's hard to say immediately because the proof is not completely written up, and it involves a lot of cases, as I understand it. So
okay.
Yeah, but that seems to be the key property that makes it possible to prove something like that for m=3, where it's not possible to, or no one's figured out how to prove that even for m=3 on grids.
Okay. And I guess another question, I mean, there are many different transition functions you could look at, right? And each of them would give you some kind of a state space, which is a
yeah. And so some others,
have other functions been studied?
Yes, the main the precursor to Recom is called the flip chain, and in this one it doesn't make sense when you have exact balance constraints, but if you have some epsilon balance constraints, it does. You just take one census block, one vertex at a time that's on the boundary, and flip it to the other thing that some other thing that it's touching. So some valid move where you're only changing the assignment of a single vertex.
I mean, you could do two of those at the same time, and then it will be
yes,
balanced.
and so that's called the swap chain. That's another one. And then you can maintain balance. These things do not mix. They like I should show you I don't have the picture on hand, but you can look at like starting from a grid partition where you've got things just completely in stripes, and you can look at after thousands, tens of thousands of steps. Recom is like already, as I said, like after 2000 steps, looks nothing like the original partition. Even after hundreds of steps for smaller instances, it looks nothing like the original partition. The flip chain, it basically makes all the districts snakier. snakier. So like really non-compact and looking basically in the same place where they started. Like it's easy to identify where the strips started from looking at the partition after thousands of steps. So it's a really bad from empirical perspective. These other Markov chains are really slow mixing and non-compact. It's a double whammy of doesn't satisfy any of the properties we want. So that's why Recom is so great.
And what is known about the connectivity of the state space for these other transitions?
So there's yeah, flip is still not known. I mean these things are special cases of Recom, right? So still nothing known.
Right.
Yeah.
So if it's disconnected in Recom, it should also be disconnected in those,
Yeah.
right? Oh, okay, I see. Okay, thanks. Are there any other questions? That doesn't seem to be the case, so thank you again. I will